Okay, we are still in example 11.2. So I just want to explain you a little more about how this component and this component become equal to 0. Okay, so this component, we need to make sure that this component is not diverging. Therefore, the this t should be have negative value. Therefore, this s, which is equal to epsilon, this is in complex form, j omega, and we use the real part only. Okay, so when the epsilon is a negative value, what will happen is e, when negative, any negative value, for example negative 1 t, this one will be e power of t. So when t is going to infinity, this one will be going to infinity. So we don't want this kind of case. Therefore, we decide the condition is to be like this, where the epsilon should be bigger than 0. Okay, so that when epsilon is bigger than 0, so for example positive 1, so this one will be negative, and it will be 1 over e power of infinity. So this one will be equal to 0. So that's why when we set this condition, these two components will automatically become 0. Okay, so that's why this is the only component left in the function. Okay, so now we will go to the next example. Example 11.3 and 11.4 is also the derivation of formula, but I want you to do it yourself. You can try it yourself. So we go to the section 11.2.3. We want to learn about the existence of Laplace transform. Again, it is related to this condition. Okay, so we have learned a finite limit exists only when epsilon or the real part of s is bigger than 0. So when the limit is 0, so that means the component will be, for example, this component will be 0, these two components. Okay, but this 0 value is not always 0. This value depend on the type of function. So what is this epsilon actually? We call it abscissa of convergence, epsilon c. So this value actually is the abscissa of convergence. So this value can be changed, according to the type of function. So the range of the Laplace transform is also this equation. So this can be any value, right? So now we go to the first property of the Laplace transform. The first one is the linearity property. So this is the concept that we need to learn. So it's like an operator. So when the function consists of two functions with alpha and beta is a constant, so it is equal to different component of the operator, where the first one is the operation of f function, and the second one is of g function with the constant at outside. Okay, so this is linearity property of Laplace transform. Okay. And what about the condition? What about the abscissa of the convergence, epsilon c? So if for function f, the abscissa is epsilon f, and for function g, the abscissa is g. Therefore, how to decide the abscissa of convergence of this combination of function? Okay. So, actually, this is the case where the abscissa of convergence epsilon c is actually, we pick the bigger one between the two. Or if this function is consists of 4 function, we consider the 4 function abscissa of convergence, and we pick the biggest one. So the biggest one is the abscissa of convergence for the combination of function. Okay. Alright. So we go straight to the 11.7 example. So now we have quite complex equation. So actually this one is not fraction. So this is f function, this is g function. Okay. Okay, so we have 2 functions, 3t and 2 exponential 3t. So how to solve this type of equation? How to transform this function is by transform individually. So we transform the first one. So 3t. So for t, we consider t. So this is the solution. For e power of 3t, this is the solution. Okay. And these are the condition according to the okay, for this one, why it is bigger than 3, you can learn in example 11.3 or 11.4. Okay. So when the function is in exponential form, the value of abscissa of convergence, epsilon c, can be different. So it seems that when it is 3, so it will be 3. Okay. But you need to learn how to get that. Okay. Now we combine. We get these 2 components already. So we use the linearity property. So we will have this function. So we put the function inside here, and also the constant. So constant is 3, constant b is 2. This is the answer from here. This is the answer from here. Okay. So we simplify it. So what is the abscissa of convergence? We consider these 2 value. Which one is the bigger one? 3, right? So this is the condition, and voila, that is the solution for example 11.7. Okay. Now we learn the second property, which is the first shift property, or we can also call it exponential modulation. Okay. Whenever a function has this kind of form, where the function is multiplied with an exponential, so what we can do is, actually we can transform the function first and find this big F, and then we consider the value of a of the exponential and we add it right here. Actually, we subtract the s over there. And what about the abscissa of convergence? What is the condition? We just add the epsilon c right here, the one that we get from the transform of the f function. We add with real part of a. Okay, usually real part of a is a, which means, for example, if a is 3, so the condition is we add 3. Okay, you will learn that more clearly inside the example. Okay, now we go to example 11.10. Okay. Before that, this is another form that we can use to describe whenever there is exponential this kind of equation. The Laplace transform of exponential multiplication. So we want to determine this kind the exponential equation multiply with sine 2t. Okay, so first of all we solve sine 2t first, which is right here. Okay, now this is the formula. You can get the formula in example 11.3 or 11.4, and this is the condition. Okay, so remember, this is condition only for sine 2t transformation. Okay, so now we want to consider the whole function. So this is the formula that we have, the property that we have above. So we just replace s right here with s minus a. So a is what? A is negative 3. So I'm not sure whether this is positive or negative, but you can check it in example 11.10. But when we replace it, this is the only part that we replace by adding the minus a right here. Okay, and I think it is positive because everything right here is positive. So my mistake right here. So when a is equal to negative 3, so where negative, it will become positive, right? So this is the final solution. Okay, but remember, it is compulsory to put the condition of the Laplace transform. So we consider the condition abscissa of convergence. So this is the formula given right here. Okay, we use it and we add a is negative 3, so actually we minus 3. So since epsilon c is equal to 0, therefore this is the new condition for the function. Okay, so there you go. That is the final answer for example 11.10. So that is the two property that we learn right now. So now we can go to the third property. So the third property is derivative of transform property, or we can call it multiplication by t property. Actually, we just multiply the function with t. Okay, so if f is the transform of this one, the small f function, and the condition is this epsilon c, then if we add t power of n, where n can be n is integer, therefore the Laplace transform that we will have is this formula. Okay, so depend on the value of n right here. So when n is for example 1, so e power of 1 dfs ds. So this is the Laplace transform. So we need to do some differentiation. But if n is equal to 2, we need to calculate second derivative. Okay? Hopefully you get that. And what good thing about this property is the condition, the abscissa of convergence is not changing. Even though we add any value of t, I mean any power of t at the side of the function. So the abscissa of convergence is similar to the function right here. Okay, so we go to the example 11.11. So we have t sine 3t. So we have t power of 1 right there. So what is the first step is we transform sine 3t first. So this is the formula for sine, how to transform sine. So after we transform it, we get this answer, and the condition is this one. Okay, and then we use this formula to solve the overall function, which is right here. So since the n value is equal to 1, therefore we put everything, we replace all n equal to 1. Okay, so we will have a negative 1, and we differentiate this function with respect to s, and this is the outcome of the derivative, and the condition is the same, similar to this one. Okay, so now we can try the next example 11.12. So right now the function is e power of t, and we have a multiplication of t power of 2. So first of all, we consider the function first, e power of t, and we know that the formula is this one, and the condition abscissa of convergence is 1. Okay.